Chapter 3 review, and we are going to do 2, 4, 6, and 10. 2, 4, 6, and 10. Okay. So number 2. So we have the age distribution down below, and the first time I looked at this, it appeared to me as though it was 2 different data sets, but it's just the same data set. You have to be careful in this case because the class intervals are not all the same size. If the class intervals are the same size, then you can just graph the height as the percentage. But when they're not, then it gets a little bit more complicated. So I need to go all the way to 75. 5, 10, 15, 20, 25, 30, 35, 40. 75. Right? So my first one is from 0 to 5, and then to 15, and 20, and 25, 30, 35, and then it jumps to 45, and then to 55, and 65. Did I mess up? 30? Maybe I just counted wrong. And then 75 and older. Okay, so here are the class interval divisions. Okay, and when you do your class interval divisions, you need to figure out what the tallest box is going to be. So, which box is going to be the tallest? Either the 5 to 15 or the 45 to 55. Okay, and how tall is the box going to be? Well, we know that the area of the box is 14. Okay, but what's the width of that box? 10. So the height would be 14 divided by 10, which is 1.4. The 35, oh geez, I skipped right over that. Sorry, 35 to 45 is 15. 15 divided by 10, 1.5. So I'm going to go up by 1/2. So 0.5, 1, and 1.5. Okay? And I know that the 35, 45 goes all the way up to 1.5. Okay? So this box here contains 15% of the total. And you can see that 15% by taking the width, 10, and multiplying it by the height, 1.5. Now, what if I don't worry about class intervals? Watch what happens. So 0 to 5 and 5 to 15. What if I graph the 0 to 5 up here at 7? Okay. And then I graph the 5 to 15 up here at 14. Why is that wrong? The red box is 4 times bigger than the black box. But in reality, it should only be twice as big. So you can see that I can divide this into 4 equal pieces, and this is the same as all 4 of those. So you can't simply label the y-axis with these unless there is one case in which you can do that. If all the class intervals are the same width, then you don't need to worry about it. Okay? But if they're not the same width, and even if they are, it's a good idea to graph it the right way, because then you can see the percentages. So if we go, where did it go? There we are. So here, the 0 to 5 has to take up 7%. So I'm going to take my block, which is 7%, and divide it by the class interval width, which is 5, and I get 1.4. Which means this particular block goes all the way up to 1.4. Okay? And then my next class interval is 5 to 15, which has a width of 10, and the area is 14, so what's the height? It's also 1.4. So this one is equal to 1.4. What about, oops, this is all one block, sorry. What about the next one? In fact, the next 4 are all 1.4. So that one, and that one, and that one, and that one are all 1.4. Okay? What about 45 to 55? It's 14 divided by 10, which is 1.4. And you can see this block is equal to this block. And those blocks are twice as big as the narrower blocks. They have the same height, but they contain twice as many people because they're twice as wide. All right? And then what about the 55 to 65? Contains 10%, which means we're going to go up to 1. So 10 times 1 is 10%. And then the 65 to 75 contains 6. So it would be 6 divided by 10, which is 0.6. And then it tells us what to do with the rest. What's the upper end on this? It tells you in the problem, stop at 85. If I stop at 85, what's the height of the last block? Would be 0.6 divided by 10, which is, or sorry, 6 divided by 10, which is 0.6. And actually, that's supposed to be the same size. I didn't draw that very well. Okay. So, A, are there more children age 1 or elders age 11? Whoa, 71. I'm really old. Are there more 1-year-olds or 71-year-olds? Can we tell? We can't really tell, right? Maybe there are no 1-year-olds, but there are 0s and 2s and 3s and 4s. Does that make sense? We can't really tell. If we had to guess, what would our guess be? Our guess would be 1-year-olds, but we don't know for sure because there might not be any 71-year-olds. So we don't know. Are there more 21-year-olds or 61-year-olds? Once again, we don't really know. What would our guess be? 61, and maybe they're... Anyway. Are there more people aged 0 to 4 or 65 to 69? 0 to 4. Can we be sure on that one? Yeah, because as soon as they hit 5, they get bumped into the next column. So 4 years, 11 months, 30 days or 29 days and 23 hours, something like that. So C, we can be sure. Because as soon as you hit 5 or 70, you bump over to the next one. Oh, wait. Okay, D, well, 65 to 75. I don't like these questions. Anyway, the percentage of people aged 35 and over is around, how are we going to get that? We could add up that whole right column. Or, what else can we do? We could look at our histogram, and there's the divide line. What do you notice? It's about half. Yeah, see? Yeah, because it doesn't say 75. So, I guess what they're saying is those class intervals are evenly distributed. But technically, we don't know, right? So, if are there more people in this column or in this column? And the answer would be 0 to 5. But again, we don't really know because we don't have enough information. But I guess the book must be assuming that each class interval is homogeneous, right? That each class interval is evenly spread. If a class interval is not evenly spread, you need to redefine your class interval, right? So if you have lots of 3-year-olds and no 4-year-olds and a few 5-year-olds, you're not going to put all of them in one block, right? Because that will average it out when you should have a peak and 0 and then a small level. So maybe we can assume that all class intervals are homogeneous. Okay, number 4. The figure below is a histogram showing the distribution of blood pressure for all 14,000 women in the drug study. Use the histogram to answer the following questions. Is the percentage of women with blood pressure above 130 around a quarter, half, or three-quarter? Quarter. Okay. It's about 25%. Is the percentage of women with blood pressure between 90 and 160, 150, or 99? 99. Okay, there might be somebody less than 90. It's hard to stay alive if you don't have blood pressure, right? You got to have some. So below 90 gets a little bit dangerous. And then above 160, it's also hard to live. If your blood pressure is above 160, blood vessels in your brain tend to break. They can't hold that much pressure. And when a blood vessel in your brain blows, it's called an aneurysm or a stroke. Yeah. Because when blood leaks in your brain, that's a problem. It puts pressure on things. And if the pipe's broken, then the bathroom isn't getting the water. Hey, what's up? Yes. All right, C. In which interval are there more women? 135 to 140 or 140 to 150? So 135 to 140 is taller, right? But 140 to 150 has a greater area. So it would be 140 to 150. Number 6. Hypothetical. So we have a study of 100 people. They have their heights measured to the nearest eighth of an inch. Oh, did I miss one? Oh, sorry. Ah. Okay, 4D at the top of page 52. Which interval is more crowded? 135 to 140 or 140 to 150? How do we tell how crowded something is? How tall it is? The height. So it would be 135 to 140. On the interval 125 to 130, the height of the histogram is at about 2.1%. So what percentage of women fall in that category? How would you figure that out? If it has a height of 2.1, how do we calculate the area? Multiply it by the width, which is 5. 2.1 times 5, 10.5%. Okay, F, which interval has more women, 97 to 98 or 102 to 103? This is the same problem we ran into before. We don't really know, but I guess we're just going to assume that all class intervals are homogeneous. So 97, 98 or 102, 103? 102, 103 is a lot higher. And then, which is the most crowded millimeter of all? If you had to select just one, 100. Well, you got to pick 1 millimeter. So 1, maybe 18. 119, maybe 117, somewhere in there. You could make an argument for any of the ones between 115 and 120. Okay, number 6. In one study, 100 people had their heights measured to the nearest eighth of an inch. A histogram for the results is shown below. 2 of the following lists have this histogram. Which one and why? So we have 1, 2, and 3. 2 of them fit the picture, and 1 of them does not. So, number 1, 25 people, 67 inches tall, 50 people, 68, and 25 people, 69. Does that histogram fit 1? Yes. Right, a quarter of the people at 67, half at 68, and half or a quarter at 69. 10 people, 66 and 3/4. 15 people, 67 and a quarter. 50 people, 68. 25 people, 69. Does that work? It does, because the first 2 class intervals would be combined into the 67, and they would be a quarter. Okay, so 3, 30 people, 67, 40 people, 68, 30 people, 69. No, why not? Well, they don't fit the numbers on the left, right? They match up with 25 and 50, and the other problem is the middle one would have to be twice as tall as the first and last, and that's obviously not the case. And number 10. The table on the next page shows the distribution of adults by the last digit of their age, as reported by the census of 1880 and 1970. You might expect each of the 10 possible digits to turn up 10% of the people, but this is not the case. For example, in 1880, 16.8% of all persons reported an age ending in a 0, 30, 40, 50. In 1970, this percentage was only 10.6. Draw histograms for these 2 distributions. Why might that be the case? In 1880, why were there a lot more people that had an age that ended with a 0 than in 1970? What's that? Any idea? 90 years later, why would there be fewer people that ended in a 0? Do we think that the numbers should be equal? Should they all be 10%? Should be pretty close, right? If you grabbed 100 people, how many would you expect to have a last digit that ended in a 6? 10 of them, right? 10 of them would have a 5. Um, and then in 1970, it's not perfect because everybody starts at 0. So 0, 1, and 2 are more likely than, say, 8 and 9 because some babies die. Some people never make it to 70. They make it to 65. So the lower numbers will probably have slightly more. But in the 1880s, some people might not have even known their birth year. And so they just said, 20, 30, right? So they just they weren't totally sure, and it was a lot easier to just go by a decade. Okay, so all of these class intervals are the same width, so we can just graph the heights. All right, I'll let you do that. In 1880, there was a strong preference for 0 and 5. How can this be explained? Maybe they weren't totally sure. Or in the 1880s, specific ages might be less useful than they are today. Certain things happen exactly at 16 and exactly at 19 and exactly at 21, and people just rounded to the nearest 5 back then. We pay a little bit more attention to our exact age now than we used to. Are even digits more popular or are odd ones? So let's compare it. 16.8, 6.7, 9.4, 8.6, 8.8, 13.5. What do you notice about even and odd? It kind of bounces all over the place in 1880. But what about 1970? More the even, well, that also kind of bounces around. Yeah. All right. That's it for chapter 3.